in Bonn, there is a joke about a tier. A tier would give traditionally always the first talk of the opening talk of the Arbeitstagung. He did this for over 30 years. And the joke was he would every time he would talk about the index theorem. But he never said the same thing twice. So I'm fully aware that I was invited a few years ago and talked about something that was kind of looks like the same thing. But I'm going to say, so despair not, I'm going to say new things today. So that's a joint talk with David, and it's a joint project, David Miyamoto. And I'm just going to state the goals and then hand over to him for the first part. So the goal is to show you that there is a Lie functor, not quite Lie theory yet. That would be claiming too much. It would, ask questions about integration, but at least that's what we have, a Lie functor from diffeological Lie groups, diffeological groups, let's just say, with a little extra condition to the algebras, and for a diffeomorphism group of a manifold, so that's the really new thing. What this gives you is the Lie algebra of all vector fields. This works if M is not compact and there's no condition on the vector fields whatsoever. So that's sort of the punchline. Okay? And so the structure of the talk is, so first, that's David's part. David will review a few facts about smooth structures on with n. I mean, what do we know already? What has been done here? There's no better place to talk about this than in Vienna, because people know what's everything that's to be known and have worked this out. Part two is constructing that Lie functor. And this is not just for better pedagogic reasons, but that's how we did it in 2 steps. So first, we took an earlier work by Rosicky and extended this and give a Lie functor that works in all tangent categories. So you axiomatized what's necessary to have things like vector fields and invariants of vector fields, which works in more general settings, for example, in differentiable stacks. So we have a Lie functor of perhaps tangent categories. And then we explain what this is. And then B of these diffeomorphism groups. So or to be precise, that's the little extra thing, elastic diffeological groups. An extra punchline will be, so what is this elastic? For diffeological space, it's a lot of conditions. For groups, it's just one little condition, and we can interpret this as the vector space, the underlying vector space of the diffeological group to be convenient in the sense of Micho. Okay, so that's very nice because the way we stated and we need it is very different, but turns out to be essentially the same. So that's very, very nice. So there we touch base, with what's done here. And then the third part is to actually compute. This compute. The punchline there will be, I mean, why does this work? We have no-go theorems. The punchline will there be this the way this approach avoids function analysis altogether. So we construct this category construction. We construct it by universal constructions, certain co-limits, and then of course you have to access the geometry to actually compute it, but there won't be norms. Okay, there won't be Fauché structures, and that's ultimately what does the trick. And there's a price to be paid, and we will see, and then you can decide if you like that or not. But generally, it works very well. And I think this is the moment we hand over to David. Maybe one additional thing. Then you ask, so what's application? I mean, this is nice in itself, but what's applications of this whole machinery? So the applications came first. So this would drag me into this paper, I think, from 2013, trying to understand the diffeomorphism symmetry of general relativity. And there we had to compute the Lie algebroid of an infinite dimensional Lie groupoid, and we did this. It kind of worked out nicely, but we did this naively, and we always wondered, why did this even work? How did we get away with this naive approach? And so in hindsight, we want to understand why this worked and how and what's the structure behind it. Now we're kind of there now. Okay, David. And then as suggested by the organizers yesterday, we will hand over properly with a high five.
Something like this. Okay, yeah, so thank you, Christian, for handing off to me. And I'd like to also thank the organizers for the chance to talk here to all of you. And also thank all of you for entertaining our little Trojan horse of a talk that we're giving. So yes, my job is to review smooth structures on diffem, and it's also to introduce diffeology. We don't live in a world where I can say diffeology and everyone, maybe anyone, knows what I mean. So I'd like to have it so that you all know what I mean. So we'll begin with a table. Our goal is to understand diffem diffeologically. So let's try and establish how we understand it in different settings. So here we'll have a compact case, and on this side we'll put strategies for the non-compact case. And the first thing is, well, what is diffem? By is, I mean we want to think of it as a smooth space somehow, or a space with a smooth structure. And so what is that structure? What could it be? For the compact case, there's a pretty nice answer. There's a structure of a Frechet manifold. I think this would go back to Leslie, perhaps. So we have a Frechet manifold structure on diffem for M compact. Now, to say it is a Frechet manifold, I can tell you what the local model is. It will be the Frechet space of vector fields over the compact manifold M. And this notation xm, so I could just put down here, this is x of m for me, space of sections. When M is compact, you don't need to worry about taking semi-norms over compact sets because the whole manifold is compact. You can only worry about the degrees of the derivatives you're taking for the semi-norms. Now, this is a Frechet manifold. It is, moreover, a Frechet Lie group. So when it's a Frechet Lie group, it has a Lie algebra. What is that Lie algebra? It's going to be vector fields again. But maybe you can get the opposite Lie bracket depending on how you approach it. So I'll say it's isomorphic to the Lie algebra vector fields. And finally, when you have some kind of Lie group, you can ask about its exponential map. In finite dimensions, this is no question. They all have very nice exponential maps. In infinite dimensions, it becomes a lot more subtle, but at least in this case, the exponential map exists. So we could say exponential, and it's a question about its existence, and the answer is yes. The exponential map is just the time one flow. And I think we saw in Milan's talk a few days ago that the local model is vector fields, and we have a time one flow for the exponential map, but this exponential map is not a chart of diffem.
This is just by definition. You take ad hoc choice, or there is more principal, more fundamental property which tells
Tells
you
you
that
this
this
is
is
the algebra.
exactly.
We will come to that.
Okay.
Yes. Yes. All right. So now here's a case that is going to be more substantive. So a non-compact manifold. We'll talk about two approaches. It as a convenient manifold and as a diffeological space. Just to compare them so that we're not talking about something on an island. So for a convenient manifold, the local model, it's possible to use compactly supported vector fields for diffm as a convenient manifold. So these are convenient vector spaces in particular. And when you do this, the Lie algebra will just be the usual Lie algebra of compactly supported vector fields, and the exponential map will exist, and it will be the time one flow. So it's a very similar situation, but we do have compactly supported vector fields here. And depending on how often or how you work with diffeomorphism groups, this could be seen as a natural thing to do or not. Now,
it's a very naive question, but like, why is it problematic if you say, hey, my Lie algebra is as a space of all smooth vector fields, and then like I still have an exponential map as a flow?
well, so if you want to say the Lie algebra is all vector fields and the exponential map is the flow, then you need a systematic way to assign vector fields to groups. Right? I mean, we morally maybe want to say it is all vector fields, but we want a rigorous system that spits out that as vector fields.
I mean, like it fails to be a group. Is that your point?
Right?
So did you say like if I say like my Lie algebra is a space of all smooth vector fields, and then like and I can define an exponential map by its like time one flow?
Yes.
And did you say that like it fails to be a group?
No, but it begs the question, what is the Lie functor? How are you assigning the Lie algebras to these spaces? You could say that you want to do this for diffm specifically, but that's a very sort of particular approach. Yes, I think a lot of these questions will be answered also as I get more into the talk.
Just this suggestion, the flow is not complete, so it doesn't give diffeomorphisms. It gives local diffeomorphisms.
Yes, so yes, when you take a time one flow of an arbitrary vector field, it might not exist as a diffeomorphism of M. The flow domain might not be all of M. Sorry if I misunderstood your question. That's the problem. The flow domain might not be the whole manifold. Think of non-complete vector fields. That's what causes the problem. Sorry. Okay, so this is the convenient side. The diffeological side, which is the one that we're going to speak about, is different. First, there won't be local model. And on the next board, I'm going to explain more about that. There is no local model for diffm as a diffeological space. We don't think of it as something like a manifold. But we'll have a Lie functor, and this Lie functor will return vector fields. Now, I will just annotate this as like maybe verbally, it's work in progress, so I can't point you to some argument. And will there be an exponential map? No. And it's a strong no, in the sense that the existence of an exponential is fundamentally obstructed. So Omori, this is 81, showed that there does not exist any Lie group G with both Lie G is vector fields and there's an exponential map from vector fields to G. Both, Omori showed the existence of both of these simultaneously is not possible. So this statement here is not contradicting Omori because we just don't have an exponential map. That's the price we pay. Okay. So what is diffeology? I will do this from the ground up. So definition is from Sturio in the 80s, but there's antecedents in the work of Chen in the 70s. so he deserves a mention too. A diffeology, I'll have to write a bit, sorry if I'm talking to the board. A diffeology on a set X, it's a set with structure, is a collection of maps called plots into X. So right now, these are just maps of sets. What is U? Well, U, the domain of these maps, is some open subsets of Rn, and n greater than 0 will vary. We're going to consider a lot of maps from a lot of open subsets, not from some fixed Euclidean space. Many dimensions will appear in the domains of these plots. And there's 3 conditions on this collection of set maps. So first, it's not empty. In fact, it contains constant maps as plots. So for every dimension, for every open subset, the constant map into X, for every X in X, that's a plot. These are going to be sort of our smooth functions, or primitive smooth functions. So those had better be smooth. Second, if we're ever in such a situation as this, F here, smooth, and P a plot, this would be PF. So if you have some given plot and some smooth function between Euclidean domains, open subsets of Euclidean space, smooth is not ambiguous, it's just subsets of Rn, then this composition should also be a plot. As well. So plots are stable under pullback by smooth functions. And finally, if you have this map, which is locally a plot, then we say that P should also be a plot. Smoothness is a local notion. So being a plot is also a local notion. And these are the only axioms. So if you specify a collection of such maps with these axioms, then you have specified a diffeology on your set. Now, there's objects of a category, so we also have that a map X to Y, F is smooth if Fp is a plot for all plots into X. Yeah.
I'm sorry that
All constant maps are plots. I should put the word all here, sorry. So for every point in X, the constant map to X is a plot. So this is a covering condition for all X in X. Is this? Yes. All locally constant maps, yes. Yes. Indeed, it's one of the trivial extreme examples of a diffeology, or a corner case. Yeah. All right, and then just some notation. So we'll have the category. Diffeology.
you discovered the diffeology on every set.
Yes, I mean, we could think of it maybe in the sense that every set has some topology, the discrete one, trivial one. Well, every set also has a diffeology, the trivial one where only you take the constants. Okay. Now, these right now don't have any examples. I haven't given you examples. So what is one? A very fundamental one would be if M is a manifold. Then, what should I assign it? I could assign it a trivial one, I guess, but that's not so interesting. I already know what my smooth maps should be into M. So I'll just say that those are the plots. This collection of P is a diffeology on M. It's a canonical one in the sense that when you equip M with this diffeology, this functor from the category of manifolds into the category of diffeology is fully faithful. We capture manifolds entirely in a nice way. We don't get weird smooth maps between manifolds when we view them as diffeological spaces. Right. Now, what is sort of the use of diffeology? Well, what is good about this is that this category, unlike manifolds, will contain all subsets of things, all quotients of things, and all mapping spaces. Of course, that's the punchline for our outline, all mapping spaces. But I do want to talk about subsets and quotients because if you're not familiar with diffeology, this might be instructive. So all subsets of a diffeological space X inherit a diffeology. And the plots would be those maps into A, which are smooth or which are plots when viewed into X. So that's how I can tell if I'm a plot of A or not, if it's a plot when viewed as a map into X. And this structure is maybe innocuous to say, but has some interesting examples, which I won't have time to get into, but just to give you a taste. So if I consider the cusp in R2, it kind of looks like this. Then it inherits a diffeology. This set with a singularity inherits a diffeology. And the diffeology it inherits is a structure of the line. So it's diffeologically diffeomorphic to the real line. And this is due, I guess, a consequence of a theorem of Joris. Yeah.
Use a general example there. So it's fully faithful because you just take all plots which are bijective with invertible inverse. This gives them atlas or maximal atlas.
Yes.
And the morphs are the same.
Yes. Yes. Exactly. Okay. So this is some counterintuitive behavior of subset diffeology. This is true for you. Okay, sure. So this is also work Arshan, myself, and Jordan Wash. So we sort of discovered this diffeological example by finding Joris' theorem and realizing it has this consequence that is diffeologically diffeomorphic to R 20-something. Okay. Now, that's a subset, and we see that some interesting things are happening. Quotients inherit the diffeology. So I have to mention this example. We take an irrational number and we consider this quotient of R by this subgroup, so abelian group R by this subgroup Z plus alpha Z. This is a so-called irrational torus, and these are non-trivial diffeological spaces. They don't inherit the trivial diffeology. You can distinguish them based on some property of alpha. Essentially, two irrational numbers are related by a homography, then they give the same structure on T alpha. I think for time, I can't go further into this. But you can ask me about it at some point. I'm here. Yeah.
You gave to the cusp, doesn't distinguish from a line. I mean,
it doesn't.
All curves are equal in that sense.
All diffeologically smooth curves into the cusp identify with smooth functions.
So you kind of miss some.
You don't see the singularity in diffeology. In fact, if you take the tangent space of this, therefore, at the origin, you just get R.
Okay.
But map of the embedding has a 0.
Yes.
That's how you see it.
Okay. And the final example would be mapping spaces.
That's exactly that.
Now, by map, I mean smooth map. I don't mean arbitrary set maps. I mean smooth maps here. So the collection of all smooth maps inherits diffeology. such that this exponential law holds. So it's a Cartesian closed category, or as a locally Cartesian closed category. Here. This kind of tells you a bit what the diffeology is. And therefore, if M for M a manifold, so maybe I also used M of xy for map of xy. So diff M, which is a subset of this self-mapping space, inherits a natural diffeology. Just for concreteness, I'll tell you the plots. So how can I say what a plot is? E is a plot, if and only if. Well, we want this exponential law, so it has to do with the evaluation map. It's a plot precisely if and only if this evaluation map is smooth. And that is telling me that I will wrap up soon. No, but so Christian will come back, and so yeah. All right. So then I think what I'll say next is that this diffeology can be tied back to that compact case, diff M for M compact, in the following way. So let M be compact. Or sorry, draw a line here. So there exists an embedding from Frechet manifolds into diffeology. How might I do this? Well, if I have a Frechet manifold, I sort of already know what the smooth maps should be. So it's the exact same procedure as we assigned the canonical diffeology on a finite dimensional manifold here. So we have some natural diffeology on these Frechet manifolds. And therefore, we can ask what happens to the Frechet manifold of smooth functions between M to M when we view it as a diffeological space. What kind of diffeological structure is that? This structure is precisely going to be the natural diffeology which you construct ignoring any Frechet structure and simply asking that your plots satisfy this evaluation law. And this thing here, so under this embedding, this goes to this, and that's a result of Waldorf. And moreover, a result of Christensen, Cinnamon. Yes, M is compact. Yeah, that's really important. M compact. I'm just trying to relate to the first column of my table. Christensen, Cinnamon, and blue. Key is that diff of M inside this mapping space is open with respect to some natural topology. And this then would say that if we know the tangent structure of this as a diffeological space, then we also understand the tangent structure of this. And furthermore, for diffeological groups, so Christian will tell us how we can coherently assign a Lie algebra to these things. And that Lie algebra, to sort of address the first question that we had, is going to precisely be the Lie algebra of vector fields if you take this compact M and also you take compact.
I have to make a remark here. The category of diffeological spaces is Cartesian closed and locally Cartesian closed.
Yes.
And this is just exactly the construction of the charts of C infinity MM
Yes.
that you have.
Yes.
So you say this is Waldorf 09, but it is really due to Soriot.
Okay, yes. Yeah, thank you. Yeah. Yes.
So does this Frechet condition play a role there, or could you also say take any locally convex manifold?
It plays a role, and I didn't time my thing properly, but essentially you want convenient spaces to get a nice embedding. Because you want to talk about convenient smooth maps between them. If you just take locally convex spaces that are not convenient, then you might not get a full functor. There might be more diffeologically smooth maps between locally convex spaces. So you can always assign them a diffeology, but the smooth maps are not going to be the same. Yeah. So really, there's something to say. This cannot be said in the convenience setting. And
I have another question. We just discussed in your Neal parabola. Okay.
yes.
So if you forget about embedding the Neal parabola into R2, you just look at the Neal parabola, then you cannot distinguish it from R in
Yes.
diffeological category?
Yes. Yes. Diffeology does not distinguish this subset from R. It does not.
So your nice embedding goes down with mild singularities. Your embedding from manifolds to diffeologicals.
No. There's no issue here, really.
No, that's clear.
Yeah.
But if you go from manifolds to slightly singular spaces, your fully faithful functor is not more fully faithful.
Well, you see,
Can I
what
comment to
other
that?
structure might we put on this? To say it's singular, right? Like, so basically, what would you put here, I guess, is the question. And so the cusp doesn't really live in any category that I know of.
Of course.
So then...
So it lives in myriads of singular spaces. I mean, that's clear. There are a lot of categories where this is required.
Yeah. But in any case...
Sorry, can I just comment to this? What Joris really proved is if you have a function f such that f square and f to the third power are smooth, then f is smooth. This shows that this O'Neill mapping, it's not an immersion, it's initial. And therefore, the structure, the differentiable structure, whatever structure you look at, that it inherits from R2 is unique. And it is the same as R2. This follows from the O'Neill, from the Joris theorem. And the Joris theorem is also true for f to the power p and f to the power q. If p and q are relatively prime, then you have the same thing.
Well, I don't understand. I mean, a Neal parabola is not R. I mean, there are many categories.
Yeah, but
where it's not R.
The smooth structure that it inherits from the embedding is unique, and it is R.
Okay, we have to discuss.
So, okay.
Spaces that.
So,
It's not relevant.
why diffeology?
It's just wrong.
I'm not a diffeologist. I don't want to go into these philosophical debates that this is the better generalization of manifolds than others. Diffeology, you shouldn't think of this manifolds with a little bit of, singularity possible. It's extremely general category. It contains topological spaces, blah, blah. So it's one of these settings that are so popular now. I don't know. Of course, we have the traditional Check-Chen, Fröhlicher, convenient, but now we have derived manifolds, chronological manifolds, pre-sheaves, blah, blah, whatnot. So why diffeology? Well, ultimately, it has to prove its worth and what you want to do with it. But in this business here, of course, the observation starts. I guess that's what Soyuz motivation is, that you can kind of naively construct the bracket, Lie bracket in a group, in a diffeomorphism group, by just using paths. I'm just reminding you. So if you have smooth isotopies, and so if you take, let's say you apply them, so now you get a path in M, you differentiate, equals 0, so that's some tangent vector at M, and you do the same thing for phi, another one that gives you smooth vector fields. And in the non-compact case, these things don't need to be flows, right? They don't need to have the semigroup property, the group property on T, could be any paths. And then what's the bracket? Well, it's the group commutator. And it's the second infinitesimal neighborhood of the group commutator. So this inverse, you apply the whole thing to M, differentiate with respect to S, T, do it at T, S equals 0, T equals 0, you will get pointwise bracket. So somehow there's a computation that produces the bracket that just uses these smooth families, smooth paths inside R, which is smooth homotopies. So that's how you would explain it to a student in an undergraduate course, like in a physics course. It's where you can't like talk about Fichet or anything complicated. So now, why does this work? So that's one of the reasons, one of the things we want to understand. And this works also, as I said, in non-compact. But it looks like a bit of a naive computation, and this you want to make this part of a, let's say, Lie theory, like proper structure, functor to Lie algebras and so on. And so that suggests that diffeology here is a good framework to consider this question. Okay, good. So now I'm going to take a step back. So why, if Soriot started with this idea and this motivation, why don't we have this Lie theory? The issue is that, let's say, at least historically in diffeology, the tangent functor itself that we need to do this here in diffeological spaces is what's considered to be a complicated subject. There's a whole zoo of those, and they all don't quite work the way they should. And that's maybe part of our solution. Okay, so now we take a step back to, obviously there is an issue with the tangent factor, and take a step back and go into category theory, some category theory, to understand what is the structure really needed for this Lie functor, like abstractly, like not looking at the specific geometric situation, so that you can associate to a group, it's Lie algebra of invariant vector fields. So what we need, so let G, well, with some application and group identity E, what? Well, just a group object in some category C. What do we need to associate to it its Lie algebra? So one, well, we obviously needed a tangent functor, so we need tangent functor. So let's say we view the, for reasons to be seen, I think we view it as an end functor, and the bundle structure is an extra structure on the functor. We have tangent functor, and then it needs to have the property. So to have talk about invariant vector fields, we need to have an action of G on TG. So we have multiplication. We need to apply differentiate. And now to get an action of G on TG, this needs to commute with the product. That's a very minimal condition. And then we precompose with G zero section. So that's another thing we now need. The identity TG. So that's the zero section on the bundle. Okay, so now we already see we need a few structures. We need zero section on TG, where now the zero section is GG and has to satisfy certain properties. So this thing is the left action of G on TG. So that's the easy part. The more complicated part is the brackets. And So vector fields in category, that's a kind of evil thing, because there is no functor of vector fields. It doesn't help if you put your algebraic geometry hat on. If you define vector fields without tangent functor, you say, oh, tangent functor is evil. Say it's derivations of the structure ring, doesn't help. Derivations of the ring of functions on a space is also not a functor. So this is not something we can easily integrate into these thoughts. So how do we define vector fields and their brackets in a natural way that fits into a categorical framework? Fortunately, Rosicky has solved this problem. So he has isolated the structures, the properties and structures that a tangent functor in manifolds has that are exactly needed to find the bracket that satisfies Jacobi and what you need. So here's some point I'm going to ask him, but I think here is how he came up with it. So I'm going to go deductively from our cherished formula of vector fields in local coordinates and pick it apart in a sort of somewhat categorical way. So this will be easy. Okay? So don't be scared. So we have V acting on W minus W V. Well, the usual thing that you learn. So, okay, what's the ingredients here? First, if we write like this, we've already identified this in local coordinates, that there's a tangent vector, so that there's a base point and the value, and we just talk about the values, and it's in Rn, but the base point of a tangent bundle, that's also something in Rn, an open neighborhood, should be distinguished. Okay, that's two things.
Lacking in your
sorry. So let's add in the base point. Let's say v of x is really like some vi of x. So some base, the base point. Okay. Now somehow one vector field acts on the other, which means we have to differentiate this vector field and then insert the other vector field into the differential. That's what that means. So let's write this differently. So if we differentiate TV, so now it eats x and a tangent vector, the differential of that map. And well, it's just, well, it's base point. Now it's a section. So on the base point, the tangent is still the identity. Right? So it's ui. Now the interesting part is, of course, that. How do I want to I try to get my indices straight to make it look nice at the end. Ji. Okay. And now, what I said, if we insert W into TV, that should somehow produce this term. Right, like this. TV, and then we insert W in it. So again, sorry, xi, vi. Now this is the identity, W, I, and now the desired term. Okay, and now it seems, so far we have used the tangent factor. So TV and composition. Now we want to subtract the two, but if you do this, you sub V and W, these are in the wrong place. So it would be X, W, V, and then D, W, V, Y. So you can't subtract them because they don't live in the same fiber. What you need in addition, you need to exchange these two guys.
It should not be the same, of course. Xi, Vj, etc. Yeah? Because it suggests that this is the same index.
I assume that everybody knows how to work in local coordinates. It's a heuristics. I could just give you axioms. I'm justifying the axioms. Okay? And it's not a proof or supposed. Okay? That's that's what I'm doing. So here, the point is that we need this operation that flips the two differentiations. So it's kind of Schwartz, you can exchange the order of differentiation. The whole thing lands, of course, so that's a map from x to t squared x. And here, you somehow need to be able to flip these two guys. Okay? So t, it's now, well, we do it on a group or on a space, it doesn't matter, but let's say on a group. So I started for G, and it does, so let's drop the indices, okay? You have x, the tangent vector, then the base point of the second differentiation, then differentiating twice, right? So using that t of an open neighborhood of u cross Rn, and then you do it twice, u cross Rn, cross Rn, cross Rn. That's these three guys, and you map this to x, u2, u1, and 2. Okay, so you change order of differentiation, and you check that this is a natural operation. Okay? Here it's sort of short. It doesn't change anything. Okay, good. So this we need, and now we can subtract. So now we can form, let's call it delta VW, which is T V W minus T W V, and we have to apply this tau. Okay, so now we can subtract, and we get I, and then, okay, we're still not there because that's in the vertical fiber.
I should be 0.
Oh, exactly. Thank you. That's it. This would have been catastrophic. Thanks to the experts in the audience. So that's 0, right? As we subtracted W from W. And now this is the vertical tangent fiber of the second tangent bundle over TG. So what we now need to use, that we have another natural transformation which maps, so that's two tangent vectors on the same base point, x, u, let's write like this, u, x, u prime. This maps that to these three copies, x, u, 0, prime, and that's again natural transformation. You have to check, okay, like you can do this in coordinates, meaning it's compatible with base change, right? With coordinate changes. That's what I mean. And so the upshot is, I squeeze it in here, that there is this delta dw is lambda 2 of the bracket, right? Write like this. So this is, and that's unique, but it's like a preimage. So you have to identify the vertical tangent fiber, the vertical part of the tangent fiber with the tangent. So now you see.
Makes sense for any manifold, not only a group. This just says that the vertical bundle of the vector bundle is a product. Yeah, so this is.
Yes, that makes sense. It's sorry, I just wrote G because I'm for the pedagogical sense. It has nothing to do with the group structure at this point. Okay, very good. And now you've seen we've already used a bit. We have a tangent vector, we have a bundle projection, we have a zero section. We have implicitly used this subtraction, so we have a fiberwise addition or multiplication, subtraction of things. We have this tau, the symmetric structure on the powers of t, and we have this identification of a tangent space, vertical tangent space of a tangent bundle with the tangent bundle. And that's a lot of structure. And now Rosicky has encoded this in the notion of, so the upshot is that we have an abstract tangent structure that consists of, on a category C, consists of an endo functor. You have bundle projection. So let me write it like on elements. You have an addition, arrow-wise. You have a zero section. The whole thing is supposed to be group object and the category over X. You have the tau, which is from t squared x to t squared x, exchange of order of differentiation, and you have this vertical identification. That's perhaps the most tricky one. You could also just do it on 0, and that would be easier, even a map from tx to t squared x. That's how people usually frame. Plus a lot of axioms. So depending on how you count, 15-ish, it's a lot. I can't even write them down. Okay? But they encode what you need for this to satisfy Jacobi. And you see for the definition of the bracket, you need all of them. So you can't drop any. You just need this all the structure, and just that's never how you thought about computing a bracket, a Lie bracket of vector fields, but that's a categorical point of view. And showing that it satisfies Jacobi is hard.
Just postulated, yeah?
Yes, it's a definition. That's a definition.
So what is Tx for diffeological space?
That's the next part of the talk. That's exactly that. Because, okay. Good. So, and then there's a bit of additional thing that we've had to extend it a bit. So there's a condition. Let me give you the upshot. So, well, it's a definition. You can define what you want. What does it do for you? You have the condition 1, as I've already mentioned, has to be what people call Cartesian. That's easy to satisfy, has to compare with products. And 2, well, to have an actually algebra, you may have a ring object in C and a, I don't know, a kappa, a scalar multiplication to get modules. So we call this Cartesian tangent category with scalar multiplication. That has to satisfy some conditions, and then you have a Lie functor from group to Lie algebras, are Lie algebras. And that would be not that spectacular and interesting, but it brings me back to my talk 3 years ago. It works for groupoids. Now you have to have conditions on the groupoid object in C, and you get an, let's say, abstract, whatever that is, Lie algebroids. That's way more interesting. Here you have to identify the conditions for this to work, and that's work with Lori. Just was put on the archive, I don't know, barely made 24, so 29th of December. Okay, so there you can read this. And it works, let's say, nicely in the sense that you just describe the usual steps you do in a natural, in the sense of category way, in terms of these natural structures. And examples, well, will be now these diffeological groups, but diffeological groupoids, differentiable stacks. There's a lot of things you can cover with this machinery. Okay, good. So now to your question. So what's tangent category of theological spaces. This can't exist in all diffeological spaces. It's way too general. So you need to add conditions for this to work, and they're pretty strong. I call these elastic for a reason I can explain the metaphor perhaps in the break. So now, but basically we should start by defining the tangent function on diffeological space, and there's a whole zoo of them. That was very unsatisfactory when I got into the field and bugged me a lot. And so this is now really where I need this categorical approach, because people, came up with definitions and constructions and then claimed they had certain properties, and some others showed they didn't have those properties, and so on. There's like a very painful history of inching towards a good definition. And so here we put this on top. We say we want that. We want these properties. And how do we get those? What's the right definition? Okay, good. So now, let's take our cue of how we define the tangent. That's the generally local structures on a manifold. The whole point is we have charts. So now we can define, I put a little hat to distinguish it from the extensional diffeological vector space, like on a chart, image of a chart. Well, it's just U cross Rn. That's the easiest definition we can get. And what do we do then? We glue the charts together. Okay. So now, categorically, let's say Tm is a manifold. Let's put X. X is a manifold. So we take these TUs, we glue them in overlaps, and categorical way to describe this is as a colimit of the category of the charts of a, let's say, maximal atlas to make it unique, and diffeomorphisms between the domains of the. Well, in that case, it's really open maps, but let's say the category of the charts. That's just a fancy way of saying it, and what it really is, you take open subsets of Rn's for Rn. That's where you have this sort of with an Eve definition. That sits inside manifolds. And this definition here, that functor is the left can extension. So that's called T-triddle or something, sake of uniqueness. So that's the left can extension. Long I of T hat and then I. So this is going to be the idea. All we change now is we replace charts with plots. That's the only change. That's the whole, for me, that's the whole idea of diffeology. You still probe your geometry of your spaces with Rn's, finite dimensional ones. But now you probe them in a more general way. You map smooth families into it. You don't require to be a local model or local homomorphisms. So now we replace the indexing category with category. What we effectively do, we can extend one step more. Okay. This guy, T, is going to be left can extension. Okay, after I had. Now, for some reasons, people got it right for forms. They have the forms that canonically, and everybody agrees, differential forms are defined by left can extension of the theorem functor. And for some reason, this is very contentious. And it started that there was not this perspective, so people start to say, okay, it induces, like we want to have sort of a kinematic definition given by smooth paths. They define derivations of functions, and then they are supposed to be the same. That's kind of the original definition of Suyo. But the whole point of diffeology is that you have nice functions into it, and you don't require nice functions to exist on it, like the non-commutator I show. Like R divided by Q is a very nice diffeological space, and this creates problems. So this is the definition. So maybe one more thing is that's why this is sort of new, but it's, for me, the absolute base definition is you don't require the tangent fibers to be vector spaces. Why not? Well, you should not think of a diffeological space as anything like a manifold. It can be a crazy collection of points in Rn, or it could be an axis cross. So for me, at least, being back a geometry, the tangent space, at least the kinematic tangent space, should be like a local infinitesimal model of what the space looks like locally, right? And the fact that the tangent space in manifolds is a vector space, for me, reflects the fact that it's a manifold. So it looks locally like Rn, inherits the addition from Rn. But if you have an axis cross, well, what should be the tangent space at that point? Well, it should be the axis cross. So we take, it's a cone, it's an R cone. So we take this definition, we take this limit in diffeological spaces, and not in vector space, not in bundles, something. If you do it in vector spaces, you couldn't differentiate a space like this from R4 at that point. Okay, so you would lose geometric information. Okay, good. So now we have this. That's a part I will skip now. We have this. Now the question arises, well, that looks like an awful tangent function. It's not even vector space. How are we going to get Lie theory? So now, of course, the question that now we don't put this into the axioms as a condition, but now it's a property of the space. We could say, okay, what spaces have vector spaces as tangent fibers? That would be a condition on the space itself. So what's the issue? Why isn't even, why can't we throw the left Carnot extension machine onto all the structure and get something really nice? Well, the issue is that it's a co-limit, but let's say you have the addition. The Phi-wise addition of tangent vectors. Now you're constructing the co-limit. This thing maps to the x cross the x. But this is generally not an isomorphism. Because that's a limit, that's a co-limit, they generally don't commute. You do get for free that this is the same. Why? You can show that the category of plots is shifted. That's a nice, it has a nice categoric property, and shifted co-limits commute with finite products. That's ultimately the reason why this is true. But it's not like filtered or anything, like an atlas would be. Okay, good. And also, let's say t squared u is generally not t squared of x. So nothing that affects the canonical flip. So now, okay, good. Yes. So finally, before I hand over to David, let's give me a few examples. We have already seen 3 examples. Let me go really fast. For
that isomorphism. Right? It's not isomorphic.
Oh, sorry.
Yes. Yeah.
Sorry, I said the right thing wrong. Or something else. Examples for elastic space. So it's these spaces that are nice where the tangent functor behaves as usual. Actually, on the elastic spaces, you get a full Cartan calculus. You have a tangent functor. You have vector fields. You also have forms. You have inner derivatives with the usual relations. So on elastic space, you can do everything you do with Cartan calculus. You can do, which is nice. That's what I need for Lagrangian field theory. But okay, let's give you a few examples. Manifolds. Maybe I do this fast. Well, manifolds with corners. There's sort of that's a somewhat tricky thing, but it's possible. And then you have these mapping spaces. So that's the first really nice fact, these are elastic. Okay? They inherit sort of the nice properties from n, and the thing that was not known about these is it was known for compact M, but not for non-compact M, and sort of that's something you have to learn how to compute these colimits, category colimits in the situation. Okay? What else do we have? Okay. Well, of course, you can, if you have an elastic vector space, you can model a diffeological space on that. You have diffeological manifolds, meaning the elasticity, the condition to be nice, the tangent rank to be nice is local. Okay? So if you have, it's locally elastic, it's elastic everywhere, so it's fine with manifold constructions. You have certain nice categorical properties, so finite products of elastic space are elastic, arbitrary coproducts, and retracts, so mild singularities. Okay? And maybe one last thing, like that's more surprising, is there something honestly singular, stuff like this or non-commutative, they're also elastic. That's nice. That's really nice spaces from that viewpoint, which is maybe a bit surprising. Good. So now, the last and the important example is groups. Okay? So do we have to check 10 million conditions that are really hard for groups? The answer is no. Groups, maybe it's not a surprise because a group, looks everywhere the same, and you have nicer structures with a group. For groups, you only have to check one condition. And that's the following. Let me give you a definition. Like if I have a diffeological vector space in diffeological spaces, then TA is generally not has a unique map to, sorry, it goes the other way. It's generally not A cross A. Or put differently, this is a condition to be the same. So if this is an isomorphism, the Canadians call this differentiable object. It's the same as just saying that the tangent fiber of a vector space at some point or at 0 is again the vector space. If this is the case, A is called tangent stable. This is not a weird condition because you know it already from if you have CK manifolds, you have a group with a CK structure. Differentiate, you get CK minus 1. That's why you don't have a Lie algebra on CK manifolds because the bracket of two CK vector fields is CK minus 1. It's not closed. So this is one of the things that could happen here. Right? You have Rn with CK, differentiate, you'd get CK minus 1 diffeologically, and you have like the same vector space algebraically, but a different diffeology. Okay, so now proposition is a diffeological group is elastic, is good if and only if G, meaning the T at the identity of G, is tangent stable, has this property. That we need anyway, okay? Even in the finite dimension case. And additional theorem, a proposition, and that's maybe a theorem, because that's really hard to show. Additional proposition, a diffeological vector space is tangent stable, like this. So a locally convex chronological vector space is tangent stable if and only if it's convenient. So let me just say this in words. Okay? So this is how we touch base with what's being done, and that's helpful. What we don't have here in the diffeology are these groups in diffeology are no manifolds. That's what we give up. But now, oh goodness, okay. Now I'm handing over to. Should I say something about tangent space of mapping space? You can say that. Okay. Handing over back to David because now we come back to what we originally wanted. Here is nice machinery, but what is the Lie algebra